Welcome to section 6.3, solving exponential equations. Not a huge intro here. An exponential equation is one where the variable is up in the exponent. So a lot of these, we're actually going to be solving 10. The first 8 look very similar. They have a base equals another base, basically, or a power equals a power, rather. So a power is a base and an exponent. If we look here, we have bases of 2 and 8. 8's technically raised to the first. We can actually write these both as a base of 2. On this side, it's already a base of 2, but we can rewrite 8 to have a base of 2. And this is one way to solve this type of problem when possible. Not every single number would make this possible. But because 2 and 8 can both be written as a base 2, we can actually just rewrite 8 as 2 to the third because that's what it equals. This is called getting a common base. Once the bases are equal to one another, this equation has to equal each other in every way. So since 2 equals 2, the exponents have to equal each other. 4x must equal 3. So at this point, we can sort of drop the base and just set the exponents equal to each other and then solve. So x is 3/4. Now, we could see if this works by plugging it back in. So if you wanted to check your answer, sometimes it's easy to check, other times it's not. You can use a calculator. So we'll have 2 raised to the 4 times 3/4, so plugging it back in. Does that equal 8? Well, 4 times 3/4 is just 3, so 2 cubed does equal 8. So 8 equals 8. So this does work. However, this is not the only way to solve this equation. I'm going to do the second possible way to solve this equation using black. So if we have 2 to the 4x equals 8, so starting again. An alternate way to solve this is to take the log of both sides. Now you can take the natural log of both sides or the log log, it doesn't matter. Because ln is just less to write, I just like to take the natural log of both sides. So another possible way to solve is to take the natural log of both sides. Didn't leave a whole lot of space here, so I take the natural log of both sides. So these are the two ways of solving. The second way will always work. Note that this first way doesn't always work because we can't always get a common base. If this was like a 7, for instance, we couldn't. So once we take the natural log of both sides, remember we learned about the properties of logarithms, and one of the properties of logarithms was the power property that said whatever power we have up here, whatever exponent, we can bring out front. So we can really rewrite this as 4x times the natural log of 2, and it equals the natural log of 8. I'm going to keep the 8 and the 2 just in parentheses so we know what we're taking the natural log of. Again, we took the natural log of both sides, could have just taken log as well, it doesn't matter. And we used the power property to get that variable that was up in the exponent down back on the ground. Once we're here, we want to get x by itself, so we can divide both sides by what remains, which is 4 ln of 2. Using this method, you will need a calculator, and you will need a calculator for a lot of this. So in our calculator, we want to type natural log of 8 divided by 4 ln 2. I do want to point out that when you type things into the calculator, you have to be very careful. If you typed it in just like this, it will actually give you the wrong answer. And that's because your calculator will just take ln of 8 divided by 4 and then multiply by ln 2. So to show that that entire thing, 4 ln of 2, is in the denominator, you need to put extra parentheses around it. And normally, in problems like this, we do get crazy decimals. So that's why I put the squiggly approximation there. But our answer is 0.75, which is 3/4. So those are the two ways that we can solve an exponential equation when we have power equals power. If it's possible, it's much simpler to just get a common base and set the exponents to one another. But if that's not possible, this way always works. Taking the log of both sides, bringing the exponent out front by the power property of logarithms, and then dividing until you get x by itself. Let's take a look at number 2. Is this one where we can get a common base? Yes, we can actually write both of these bases as 3. This is already written as 3, and 27 is 3 cubed. So we can rewrite as 3 to the x minus 1 equals 3 to the third. Once we have a common base, we can just set the exponents to one another. So we have x minus 1 equals 3, x equals 4. In an alternate way to solve, if we start with our problem again, if we wanted to take the natural log of both sides, we could totally do that. So we'll take the natural log of this side and the natural log of 27. When we take the natural log of 3 to the x minus 1, we can bring the x minus 1 out front. We do need parentheses there to show that that whole thing is getting multiplied by the natural log of 3, and we'll have that equal to the natural log of 27. Then we can divide both sides by the natural log of 3. Once we've done that, we'll have x minus 1 equals, and then at this point, I would recommend putting it into your calculator. So I'll do that in real time. We have ln of 27 divided by ln of 3, and that gives us a 3. Then we'll add 1 to both sides and get our final answer of 4. In problem number 3, we want to think, is it possible to get the same base? Can 5 be written as a smaller base, or can 12? No. So since it's not possible to get the same base, what we're going to do is just take the natural log of both sides and use that other way of solving. Since we cannot get a common base, we only have one way that we could solve this problem, which is to take the log of both sides. Again, I prefer taking the natural log. As you get into higher mathematics like calculus and beyond, natural log kind of becomes the only log that you see. So it's good to get more comfortable using it. When we take the natural log of both sides, the reason we do that is so we can use the power property and bring this exponent down out front. So we'll have a negative x out front times the natural log of 5 equals the natural log of 12. I'm going to get rid of this negative 1 out front and this natural log of 5 in the same step. So I'm going to divide by negative 1 ln 5. When we divide by something that has more than one term being multiplied, like you want to make sure that you have that in parentheses. I recommend practicing this on your calculator to make sure that you get the right answer. So we'll have natural log of 12 divided by, in parentheses, negative 1 natural log of 5, close both parentheses. We end up getting x is approximately negative 1.543, so negative 1.54. When in doubt, rounding to the nearest hundredth, meaning 2 decimal places, is a good way to go. Now we could test this and check our answer. If we wanted to check our answer quickly, we'd have 5 raised to the negative 1.54. And does that equal approximately 12? So in my calculator, I'm going to put 5 raised to the 1.54, and I got 11.92. That makes sense because we rounded this slightly. In problem number 4, once again, we cannot get the same base. This problem looks a little bit different because now we have variable exponents on both sides. What we want to do, again, is take the natural log of both sides. The reason that we do this is so we can use that power property. I don't know why I put parentheses there. Don't need them. We can use the power property on both sides and bring the exponents out front. I'm going to distribute this negative sign through. So I'll have negative a plus 3, and that's being multiplied by the natural log of 2. And then we'll have a times the natural log of 0.1. Now in this problem, dividing both sides is not going to get us anywhere because we have a's on both sides. So what I'm going to do is distribute the ln of 2 through to both of these terms. When we do that, we'll have negative a times the natural log of 2 plus 3 ln of 2 equals a ln of 0.1. Our next goal is to get all the terms with a in it on one side so we can factor the a out. Now, normally I like getting the variable on the left, but if I do that, both of these terms with a in it are going to be negative, and then subtracting this term to get it to the right, it will be negative as well. So what I'm going to do is get both terms with a in it to the right. So I'm just going to add this term and leave everything else where it's at. So we'll still have 3 ln of 2 on the left-hand side, and then I added over that term, so it becomes positive a ln of 2 plus the term that was already there. At this point, on the right-hand side, what we can do is solve for a by factoring the a out. So we'll have the natural log of 2 plus the natural log of 0.1. At this point, we can get a by itself by dividing both sides by this entire term, ln of 2 plus the ln of 0.1. Because it's a large term, I'm going to keep it in parentheses. So we'll do the same thing on the left-hand side. Dividing here by this sum, of course in parentheses, will yield an a value of approximately negative 1.29. Problem number 5 is a lot of fun. There's a few ways to do this one actually, but I'm just going to keep it simple and keep doing what we've been doing. Now, we have this 2 out front, and so what we can do essentially, like because of this 2, is even though we have the same base, we can still take the natural log of both sides. The reason that taking the natural log of both sides is your best bet here is because we have a base of e, and natural log has a base of e automatically. So natural log and e are best friends. So if we take the natural log of both sides, it'll look like this. And this is the natural log of 2 times e to the x. This is really 2 times e to the x. It's not 2e, the whole thing raised to the x. So we can't just take this x out front because this is not the entire base. Instead, we have a product inside here. And if you recall from 6.2 properties of logs, we can break that apart into a sum of 2 separate logs. On the left-hand side right now, we have this 2x, that's what e is raised to. So we're going to bring that 2x out front and multiply by the natural log of e. Over here, we are going to set this, break it apart into a sum. So we have the natural log of 2 plus the natural log of e to the x. Again, this is the product property of logarithms that says the log of u times v equals the log of u plus the log of v. Now from here, we notice a couple things. First, we know that the natural log of e is 1. So since the natural log of e equals 1, this is 2x times 1, or just 2x. Natural log of e is really nice because it goes away if it's just multiplied by something. The natural log of 2 is just a number. We'll just leave it as so. And then over here, we can bring the x out front using the power property. And then we're multiplying by the natural log of e once again. Well, what is the natural log of e? 1. So we don't even need to write it. So from here, solving for x is a breeze. We'll subtract x from both sides, and we'll get that x equals the natural log of 2. If you wanted to see what that was as a decimal, this is saying e to the what gives us 2. E is a little larger than 2, recall, so this is the number 0.69. But natural log of 2 is totally fine. In number 6, we see that we have 2 bases being multiplied, and way back when in mathematics, when you learned about exponent rules, you learned that when we're multiplying powers with the same base, we can add our exponents. It's essentially the inverse of this rule over here. And so we can write this as a single base of 3 and add our exponents. So when you're multiplying powers with the same base, you can add the exponents. The logs is just the opposite. So we'll have x times negative 2x minus 1. And we don't really need that times in there. That makes it, I think, unnecessarily confusing. So there we go. Then it equals 81. Can we rewrite 81 with a base of 3? Yes, we can. 81 is 3 to the 4th, so we can totally get a common base here. Again, we could have also taken the natural log of both sides. Either way is completely fine. Once we have the same base and they're equal to each other, what we can do is just set the exponents equal to each other. So we'll have x times negative 2x minus 1 equals 4. Again, taking the natural log of both sides would do this exact same thing, since that's just an alternate way of bringing the exponents down. Solving here, we'll have negative 2x squared minus x equals 4. Now from this point, since we have a quadratic, what I want to do is get the quadratic term positive. So if I do that, if I get the quadratic term positive, what I want to do that is add it to both sides. So if I add 2x squared to both sides and then also add the x to both sides, we'll end up having 0 on this side, and we'll have 2x squared plus x plus 4. When we have a quadratic and we want to get, in order to solve it, we want to get it set to 0. So we have a quadratic trinomial here. Is it factorable? A times c is 8, and our middle term is 1. Are there 2 numbers that multiply to 8 that add up to 1? No. So we can use the quadratic formula. We have a is 2, b is 1, and c is 4. Opposite of b, plus or minus b squared, which is just 1, minus 4 times a times c, all over 2 times a. From here, we see that we're going to end up having a negative discriminant. Because we have a negative discriminant, it's going to be 1 minus 32, so it would be negative 31. Because we have a negative discriminant in here, that means we do not have any real solutions. So there's no solution to problem number 6. Problem 7 looks a little different from what we've seen, only because we have 3 terms here, but we can very easily get this back to power equals power by subtracting 5 from both sides to start. Once we do that, we'll have 25 times 4/5 to the x equals 5. Then we can get rid of that 25 on both sides by dividing by it. We can do this because this 25 is not being raised to the x. So we'll divide both sides by 25. In doing that, we'll have 4/5 to the x equals 1 over 25, which is 1/5. Now, in this case, it looks like we could maybe write this as a common base, but it doesn't end up working out really. So we do have to take the natural log of both sides. When we do that, we can bring that x out front. That's why we did it. So we'll have x times the natural log of 4/5 equals the natural log of 1/5. Then we want to divide both sides by the natural log of 4/5. If you prefer to use decimals when entering this in your calculator, that's fine. These are pretty easy to know the decimals of. Every 1/5 is a 0.2. So this is the natural log of 0.2 divided by the natural log of 0.8. We end up getting x is approximately 7.21. Problem number 8, we again have e equals another e, but what we can do is, if you'd like to simplify both sides so we don't have coefficients on both sides, you totally can. And in this case, it works out nice. We can divide both sides by 8. That makes things look a little bit simpler, rather than dividing by 24, which would give us a fraction out front. Either way makes things simpler, but this, I think, makes it a little bit easier since we'll have whole numbers out front. So 24 divided by 8 is 3. Again, makes it a little simpler than having a 1/3 on one side. So this is very similar to the problem we did earlier, I believe number 5. We do want to take the natural log of both sides. So when we do that, we'll have the natural log of e to the 0.2x equals the natural log of 3e to the negative 6x. Again, this is 3 times e to the negative 6x, so we can't just bring that negative 6x out front because 3e is not the entire base. We can rewrite this, though, instead as the natural log of 3 plus the natural log of e to the negative 6x. And we can do that because of the product property of logarithms that says the log of u times v equals the log of u plus the log of v. This side, we can bring that 0.2x out front. And then it's multiplied by the natural log of e. The natural log of e is just 1, so it's multiplied by just 1, so I don't need to write that. So 0.2x equals the natural log of 3. That's just a number. And then here we can bring that minus 6 out front, so it'll be minus 6x I meant, times the natural log of e. The natural log of e is just 1, so again, we don't need to write it. So I'm going to add 6x to both sides, so we'll have 6.2x equals the natural log of 3. Dividing both sides by 6.2 gives us the natural log of 3 over 6.2. And putting that into our calculator in real time will give us approximately 0.18 when we round. Numbers 9 and 10 are going to be a little bit more complex. And these are the 2 problems that look like your Wellness Wednesdays problems. These are going to be, well, let's take a look at why they're different, first of all. So this problem is different because we cannot get rid of this plus 6. We have a power equals a power and then plus some extra thing. So because we have 3 terms and we can't just get it back down to 2 easily through any sort of subtraction or addition, we have to use some sort of substitution. And luckily, we see that both of our powers here can be written with a base of 5. So I'm going to just go ahead and rewrite 25 as 5 squared, or 5 squared, and then we also have the x up there, so it's 5 to the 2x. This is an alternate way of writing 25 to the x is 5 to the 2x. Then we have still equals 5x plus 6. Now, I wrote this as a quadratic in disguise, and that's because we have something squared, we have something just like to the first, 5 to the first, sort of, and then we have a constant term. That looks like a quadratic trinomial. Let's get it set to 0. So I'm going to do two things in this next step. This 5 to the 2x I'm going to rewrite. Because multiplication is commutative, we could also write this as 5 to the x times 2. So this could be written as 5 to the x, and then it could just be written as squared, since these two are being multiplied anyway, the x and the 2, either way. I'm subtracting 5x from both sides and also subtracting 6, so we can get this to 0. So all I've really done is gotten these three terms on one side to equal 0, and also I've written 25 to the x as 5 to the x squared. Now take a look at what we have. We do have a quadratic in disguise. We have 5 to the x being squared, then minus 5 to the x minus 6 equals 0. We can use substitution and let some other variable, I'll let a, I think your book uses u, but I'll let a equal 5 to the x. The reason we do that is because we can then replace it. So every time we see 5 to the x, we can write an a. So we'll have a squared minus a minus 6 equals 0. From here, this is a pretty easy quadratic trinomial to factor. Two numbers that multiply to -6 that add up to that -1. We'll have a minus 3 and a plus 2 equals 0. That means that a equals 3 and a equals -2. Now, the only problem is that once you use substitution, you can't just like get our, we don't necessarily care what a equals. We need to solve for x because that was the original variable. So we're going to do what's called back substitution. So because we let a equal 5 to the x, over here in blue, what I'll do is replace a with what we saw that a equaled. It equaled 3 and -2. So back substitution will give us that 3 equals 5 to the x. Again, letting a equal 3, that's what we found it to be. And then also -2 equals 5 to the x. And these look like problems we know how to solve. For this first equation, we can take the natural log of both sides. When I take the natural log of 5 to the x can come out front. So dividing both sides by ln of 5 to solve for x. We'll have that x equals the natural log of 3 divided by the natural log of 5. The natural log of 3 divided by the natural log of 5 equals approximately 0.68. So that's one answer. Let's see if we have another answer. We want to take the natural log of both sides, but here we run into an issue. We cannot take the natural log of a negative number. The domain of a logarithmic function, what can be input into here, remember, has to be greater than or equal to 0. So in your calculator, if you typed in the natural log of -2, you'd get an error. That's because we can't take the natural log of a negative number. So over here, this does not provide us any solution. Now I'm writing no solution just to this part over here. There is still a solution to this problem, and it's 0.68. Number 10 is similar to number 9 in that we again have to solve using substitution. We have a quadratic in disguise because we have two terms and one exponent is double the other one, and then we have a constant term. So what I'm going to do is rewrite this so it looks like e to the x, and then it's squared, because again, this is x times 2, this is 2 times x, they're the same thing. The second term does not need to be rewritten. It's minus 3 e to the x, and then I'm going to get that 10 over, so we can have this equaling 0. Next, we want to use substitution, so I'm going to let a equal e to the x. Because we have that squared minus 3 of them minus 10 equals 0. If e to the x was just a simple variable, this would be an easy quadratic to solve, so let's do that. Every time we see an e to the x, we replace it with a. So we'll have a squared minus 3a minus 10 equals 0. And now we have a factorable quadratic. Two numbers that multiply to -10 that add to -3 are a -5 and a +2. Solving for a, we'll have a equals 5 and a equals -2. Now, because we switched from x to a with substitution, we have to do what's called back substitution and go back to x. So the way that we can do that is note that a equals e to the x. So I'm going to replace a with 5, and I'm also going to replace a with -2. So instead of a equals e to the x, I'm going to have 5 equals e to the x, and -2 equals e to the x. So we'll have 5 equals e to the x, and -2 equals e to the x. To solve both of these for x, we'll take the natural log of both sides. Here we'll have the natural log of 5 equals x times the natural log of e. The natural log of e is just 1. So x equals the natural log of 5. If you need that as a decimal, the natural log of 5 is approximately 1.61. So, or you can just write it as the natural log of 5. So that's a solution. On this side, we want to take the natural log of both sides, and once again, we come across this issue because we cannot take the natural log or log of a negative. So in your calculator, if you attempted to do the natural log of -2, it would not work. It would say error. And that's because what's inside the log function or natural log function must be 0 or greater than 0. Actually, it must be greater than 0. So we have no solution over here. So our only solution is 1.61, or the natural log of 5.